The whole idea behind the periodic table is that certain properties of elements vary in a regular fashion. This means that we can estimate or predict these properties based on an element's location and even compare elements with each other using nothing but a standard periodic table. Most of the volume of an atom, is occupied by its electrons. So you might think that the size of an atom or its radius would increase steadily as the number of electrons increases. When we measure the radii of atoms, though, we get the results you see here. The different colored dots separate the elements into periods. So the green series includes elements from lithium to neon. The blue series is the third period from sodium to argon. The red dots represent the fourth period, potassium to krypton. And in this series, the transition elements are included. So there are more data points here than in the blue and green sets. The orange dots show the fifth period, rubidium to xenon, and then the yellow set is the sixth period from cesium through the lanthanides all the way to radon. The alkali metals have the largest radii of their periods. So these are our alkali metals. The noble gases have the smallest radii. As we move from the left to the right across a period, the number of protons and electrons in an atom increase. A nucleus with a higher positive charge exerts a stronger attractive force on its surrounding electrons, and so the electrons are drawn in. As we move down a given group, on the other hand, our valence electrons for a given atom occupy successively higher energy levels. Higher energy levels means larger orbitals, and so within a single group, atoms become larger towards the bottom of the periodic table. If we are going to use the periodic table to compare atomic radii, then it's helpful to see the trends in the context of a table instead of a graph. Atoms increase in size moving down a group, and they increase in size moving to the left across a period. Ionic size, on the other hand, is determined by two factors: the size of the parent atom and the charge on the ion. In this figure, each gray half sphere represents a neutral parent atom. The red half spheres show the sizes of the cations. Cations form when an atom loses electrons, remember, usually becoming isoelectronic, which just means having the same number of electrons, with the noble gas of the previous period. All cations are smaller than their parent atoms. The higher positive charges make the size difference between neutral and cationic atoms even more drastic. Anions, on the other hand, gain electrons to become isoelectronic with the noble gas at the end of their own period. They increase in size. All anions are larger than their parent atoms, but the anionic charge does not make as significant an impact as a cationic charge does. I'm going to pause the video here and give you guys time to answer a few questions before we move on. The next few periodic properties concern the behavior of atoms in bonding situations. The ionization energy of an atom is the amount of energy required to form a cation. The more energy needed, the more difficult it is for an element to lose electrons. This graph shows the first ionization energy for all 118 elements. This is the energy needed to turn a neutral atom into a +1 cation. you can see that it's relatively difficult to remove an electron from a noble gas. Those are all highlighted in yellow and labeled. On the other hand, alkali metals, which are labeled and red dots, become cations fairly easily. The second ionization energy is the energy needed to convert a +1 cation into a +2 cation. The alkali metals, which have one valence electron when they are neutral, have a second ionization energy that is much, much higher than their first. Alkaline earth metals show a similar spike when we compare their second and third ionization energies. In general, metals have relatively small ionization energies until they have lost enough electrons that they are isoelectronic with a noble gas. The opposite of ionization energy is the electron affinity. Electron affinities may be positive or negative because forming an anion may be an endothermic or an exothermic process. A large negative electron affinity means that an atom forms anions very easily. An atom with a smaller negative electron affinity still forms anions, but not quite as readily. And a large positive electron affinity implies that an atom won't form anions at all. The ionization energy and electron affinity are important in the formation of ionic bonds, where electrons are fully transferred between atoms. In covalent bonding, on the other hand, electrons are shared between atoms. The electronegativity of an element indicates how tightly it holds on to those bonded electrons. Electronegativity is measured on a unitless scale between 0 and 4. The higher the electronegativity, the greedier an atom is, the less likely it is to share electrons evenly with other atoms. To summarize these trends, we'll again look to the periodic table. The ionization energy increases moving up a group and to the right across a period. Francium forms cations very easily. Fluorine resists. The electron affinity increases moving down a group and to the left along the periods. Fluorine has a very large negative EA, which is low, and it forms anions easily. Francium, on the other hand, resists. And electronegativity increases as we move up a group and to the right of a period. Fluorine is the element with the highest electronegativity. It may be helpful to think of the periodic table as a very rough rectangle. Most of our periodic properties increase either up and to the right or down and to the left. The X's on each of the boxes here indicate the corner of the periodic table with the highest value for each property. Now, if you'll answer these next few questions, we'll be good.